Okay, so as we move on in this course, now that we've got sort of the kind of basics of human factors and human factors practices under our belt, what we need to do next is we need to cover and review some basic human psychology. And when I say review basic human psychology, I'm kind of assuming that you might have a little bit of background in psychology already, especially if you've taken the introductory PSY 2012 course or any number of other upper level psychology courses. But even if you haven't, well, we're going to review the basics. And the basic idea, of course, is that we can't really cover all of that in the level of detail that we might do and say back in the key introductory course, or even especially in the upper division courses. There's the upper division sensation and perception course. So we're going to do the sensory stuff first. We're going to review human sensory abilities, as noted here on the title slide. And then we'll move into motor stuff, and then we'll move into cognitive stuff, right? But each of those courses would all be things that could have an entire semester dedicated to them, and we're not going to do it at that level. Also, one key difference about how we're going to approach basic human psychological functioning, again, sensory, motor, and cognitive domains here, is that we're not going to cover it in the same way it gets covered in those other courses that tends to focus on a lot of the basic research and theories that are designed to try to understand how such systems function. Rather, we're going to focus on abilities, as noted here, right? Limitations, capacities, capabilities. What are humans capable of doing with their visual sense, for example, as for this topic? And then what are some limits and constraints on our visual ability? Because it's these sorts of things, right? Abilities and boundaries and constraints on them that really are of direct relevance to human factors. So we're going to start with vision before we move to the other sensory systems here. We got a lot to cover with vision. And we'll start with this, which is the stimulus for vision, which is the visible spectrum of light, which ranges from around 400 nanometers to a little over 700 nanometers in terms of electromagnetic radiation, the wavelength of electromagnetic radiation. So, of course, it's worth pointing out that the visible spectrum of light is part of the broader spectrum of EM radiation that exists throughout the universe. That includes the short wave stuff like gamma rays and X-rays, all the way up to longer wave stuff like radio waves. Now, we might think, why is this of interest in terms of human ability? Well, one thing to keep in mind is that there can be a variety of different wavelengths in the environment that visual systems cannot detect. There may be wavelengths emitted by light emitting diodes that our visual systems cannot detect. And those light emitting diodes could be used by technologies. And so, of course, it makes sense right off the bat to think that, well, if I want a human user to be able to see this particular light source, I don't want to use an LED that emits light in a wavelength that is outside of the range of human detectability, right? On the other hand, it might be the case that we do want to use a light emitting diode outside of the range of human sensitivity, assuming we might not want to have a human detect this, at least not without the aid of a device, for example. So what do I mean by that? Maybe, for example, you have a technology, I'm kind of making this up, honestly, you need to have working in the dark, and you don't want it to emit detectable light because maybe you want it to be secret. And in that sense, if it gives off a fairly easily detectable visible light in a dark environment, then somebody who will see it if you don't want them to see it. So by intentionally keeping the wavelength out of the visible spectrum, then it would prevent detection of your hidden device, whatever it might be. Now, You might think, well, why would you even put an LED on a device that you don't want to be seen? Well, one possibility is that maybe uh, you don't want other people to see it, but you want to be able to see this device sometimes. And so maybe if you have um, some goggles, for example, or some other kind of device that enables you to see in that spectrum, for example, in night vision, right? And so with night vision, we are able to detect some wavelengths that are in the infrared spectrum. And the idea is that not only can we see better at night using night vision goggles, but we're also able to see some things that we might not otherwise see, uh, because of the access to that particular band of the spectrum. Now, this idea that we're going to see things, and especially in the dark, relates to what we might think of as the visibility of a surface. And we want to think about what determines the visibility of the surface, whether we can see it or not, right? And then when we see it, what properties of the object can we see? And well, there's quite a bit of complexity to that, right? We can think about the idea that certainly I can perceive it, as noted on this slide, as a surface that has a certain brightness and color. But we also, vision is heavily a spatial sense, and that means that we also may see it as having a size and distance, or to simplify that, we'll call it a spatial scale, right? That there's a certain spatial scale to this, not just to the object, but really to the entire visual scene and visual environment. But we're going to focus first and foremost on those kind of more basic visual sensations about brightness and color. Now, light is a wave, and well, it's a little bit ambiguous because light acts as both a wave and a particle, and we don't really need to get into uh, quantum physics and optics and so forth at this point, or really at all. But so we might think, for example, and it's somewhat of a temptation to think that perceiving the color of an object is strictly a function of the wavelengths of light that are entering into our eyes as reflected from that object. And that perceiving the brightness is of that object is strictly a function of maybe the amplitude of the light wave, or probably more directly the number of photons and what we call photonic flux, right? But as it turns out, this is not quite strictly true, because what we're going to see is that brightness and color are really not independent dimensions of visual experience. And I have a slide, I can just jump to it real quick before coming back to explain this a little bit over here. Here are a bunch of different color patches. Now, there's a very good chance that because of PowerPoint and because of whatever monitor or screen you're using to look at this, there's some lack of balance and calibration and so forth of your screen. But one of the things that you're going to notice right off the bat is that some of these colors appear to be brighter on your screen than others. And I mentioned the calibration issue because the way this image was originally designed is it was designed to be equally bright, right, across the entire screen. So that means even though, for example, maybe that in the middle, lower middle, the lime and the lawn green patches, or to the left, the chartreuse and green yellow, maybe also the lime green, the fuchsia, the magenta, the red, the deep pink, the yellow, those kind of pop out as being brighter rectangles in the image, right? And so the idea is that because this image was created to have technically equal brightness across the entire image, there's no particular reason for those particular colors to jump out as appearing to be brighter than others. They don't reflect more light, but rather it seems as if maybe our eyes are a little more sensitive to those wavelengths and therefore detect those colors a little more easily, and therefore they appear to be a little more bright to our eyes. And so that's a crucial issue here. I'm going the wrong direction. Let me run it back to where we were. So brightness and color, therefore, will be interdependent dimensions of visual experience, right? Some colors will just be inherently brighter than others. So even though we can also define brightness by this ratio down here at the bottom, we also have to think about color, and this ratio does not really account for color. So the simple definition of the apparent brightness is defined as albedo or reflectance, and it's this ratio of luminance to illuminance. And I have to be careful not mixing up those two words, but this is relatively simple, even though this might be a technical thing you haven't encountered before, but it's almost intuitive in a way. Luminance refers to, and I've got the definitions right here at the bottom, how much light reflects from the surface to your eyes, right? So light is illuminating the environment. You have a light source like a light bulb or the sun, and that creates illuminance, how much light that we have from the light source that actually is striking the surface. And then that surface will reflect some of the light. But the idea is that surfaces don't reflect all of the light that we shine on them. They absorb pigments in the surface of any object will absorb some of the light and some of the photons, and so therefore only some percentage of that light is reflected back to someone's eyes, right? And so that's what reflectance really captures here, is that percentage of light, the total amount of light that we're shining on an object that gets reflected back to possibly someone's eyes if someone was staying there to see it. So we can imagine how this would account for a couple of things. Think about if you've ever seen like reflective tape or signs, right? So things that we oftentimes put on bicycles and cars and street signs and things like that, that are designed to have a high amount of brightness especially in dark environments, right? Because they reflect a lot and they appear to be very shiny in dark environments. That's because even in low illumination, they still reflect a very high percentage of the light that we shine on them. And therefore they have a high brightness value because they have a high albedo or high reflectance, right? Even in low light, they are easier to see. Other things in low light conditions may be more difficult to detect. And so, of course, the ability to see a surface is a function both of these things, right? How much light do we have in the environment? That is how much illumination, because in dark environments, certainly a lot of things that don't reflect very much light are going to be much harder to detect. And so if in order to see certain things that don't reflect very much light, we may need to raise the illumination levels, right? And so then once we raise the illumination levels, we might be able to start to detect some things a little bit better, right? So that's our reflectance. Go to the next page here, right? I think I had a duplicate slide in here. I was doing some editing, and this was what I had really intended to say, and I didn't delete a slide. So let's just pretend I said everything instead of starting this video over. And so I did mention the concept of photon flux earlier, right? Instead of amplitude as really the main thing that leads into our perception of the brightness of of light, but really brightness is a function of that reflectance ratio. But as again, also as noted, brightness and color are not independent of each other. So we'll go to that. And now let's go to the issue of visibility that I was talking about before, right? So as I noted, in order to make something visible, it certainly needs to reflect light, right? But we also need to have a high total illumination. So what goes on in a situation where we look out on, we're in a brightly lit environment. You can be outside in a daytime environment, and you have a really high total illumination. And so everything is well lit, but there might seem to be a sort of a paradox of sort occurring in our reflectance ratio idea, right? Because it's a ratio. And so you might imagine that if an object doesn't reflect very much light, and so the numerator of that ratio, the luminance value, is low, and we just keep increasing the total illumination, what we're doing is we're increasing the denominator. And what happens in its basic math, if you have a fixed numerator and you keep increasing the denominator, your ratio of those two gets lower and lower and lower. And so the reflectance percentage gets lower and lower and lower. And you might imagine, doesn't that drive down the albedo or the reflectance by increasing the total amount of illumination? And technically it does, but that seems to be counterintuitive because you would think, well, turning up the lights and making everything brighter, doesn't that make things easier to see? And the answer is also yes. So albedo and brightness, like I said, they don't truly capture everything about the ability to detect a surface visually. What really helps us to detect a surface is contrast, right? And that's what's going to happen, right? So imagine, for example, again, in a brightly lit environment, lots of bright lights are on, and you have lots of different surfaces around you, and some of them have high reflectance, and therefore they're going to be very bright, and some of them have a low reflectance, low luminance, right? Then they might appear very dark in your visual field, right? So that's what that reflectance ratio is really going to get us here. It's going to tell us whether or not a particular surface appears to be very bright in your environment or it appears to be very dark in your environment. And as it turns out, it is the boundaries between the light areas and the dark areas that we call contrast. And it's the ability to see those contrast boundaries, which is just a fancy way of saying an edge, right? Imagine that, right? Just simply imagine, just even on this screen, for example, you can see the letters, which are in black ink, and the background is white. And so obviously the white background reflects more light than the dark black letters, and you end up with a clear reflectance difference there. But that doesn't mean you can't see the letters. Rather, you see them very well because of the high contrast between the black and the white, right? So that's what we need here is we need high contrast, and we can always see high contrast better than we can see low contrast. So when I say here that the visibility is of a surface works best in high total illumination, that means our eyes are, really getting sufficient light to detect objects. But what's important there is that in high illumination, we can see the high contrast distinctions, but we can also see some of the low contrast distinctions as well, right? And that's harder to do in low light. So when the total light is low, what we need is in the dark environments, it's harder to see those kinds of low contrast edges, right? So in order to see an edge, a boundary between a light and a dark area in a low illumination environment, everything needs to be very high contrast at that point. So how do we measure contrast here? Well, so that is defined as luminance differences, right? So the luminance, again, is how much light the area or surface will reflect. And so we're going to use L here in our fraction as the measure of luminance of the lighter, brighter areas, like the white background of the screen here. And D is the luminance of the dark areas, such as the black letters on the screen. And so when we look at L minus D in the numerator here, what we're essentially doing is we're taking a difference, right? What is the actual luminance difference between the light and the dark? And in order to determine total contrast, though, we have to take that difference score and we have to divide it by the sum of all of the luminance coming from the entire visual scene. So when looking at this screen, there are certain luminance differences that occur at every different boundary between the letters and the background, but there's also a total amount of luminance coming from the entire screen. And that sort of is proportional to there's total illumination coming to our eyes, right? But within all of that total light coming to our eyes, there are those differences. And if those differences are large enough to be seen relative to the total luminance coming from the screen, then we can make out the differences, and that would determine contrast C, right? And so one way to think about this ratio is to think of it as a signal to noise ratio, right? The signal are the luminance differences, which would be the actual boundaries between one area of the screen and another, versus the noise, which is the total amount of light reflecting off of the screen. So we can determine essentially our contrast sensitivity function is what we also want to do here. So we can measure a threshold. So in sensory psychology, a threshold represents the weakest stimulus that you can detect. So in vision, when we measure contrast thresholds, what we want to know is what is the weakest contrast difference that we can detect. That is, if we have a black and white surface side by side, that's a pretty high contrast, right? So we would imagine clearly you can see that edge. But if we start to make the white side just a little bit darker, so it becomes, instead of bright white, it becomes kind of a gray color. And imagine if we took the black side of our black and white edge and we started to make it a little bit lighter, so that now it's also becoming a kind of a shade of gray instead of pure black. Now we have gray beside gray. And obviously at that point, the contrast difference becomes a little bit weaker and fainter, right? The L minus D difference there is getting weaker and weaker, even if the denominator is staying the same, because the denominator is the total sum of all of these two, right? And that can stay the same, and you can just decrease the light side and increase the brightness of the dark side proportionally to each other, and that would preserve the L plus D in the denominator. So what's going to happen here is that's going to lower your ability to detect that boundary, that edge, right, in that contrast. And so now the next question is if we did psychophysical research, that means presenting these different pairs of stimuli side by side to human subjects and ask if you can see the edge. What we want to do is we want to find what's the minimum amount of contrast at that edge that can be detected by a typical human observer. All right, we want to, maybe we do this with young, healthy adults because we want to detect sort of maybe peak visual function. So we want people whose visual systems have matured enough to be functioning well, but have not aged at all, so that there might be some decline. And that will give us maybe our best sense. But it's also worth keeping in mind here that even if we were to measure this kind of ability in young, healthy adults without any visual impairment, that means that finding would only apply to that particular group, and that we might also need to be concerned if I'm overall, worried about what are the ranges of human sensitivity here, then picking just the best visual abilities might not tell me the whole story here. And so looking at young children whose visual systems are still maturing, looking at older adults, looking at people with various degrees of visual impairment or have maybe a need for correction glasses of some sort. All of these factors will play into the actual numbers that you get here, right? So our what we determine as our threshold then, again, is that weakest L minus D ratio that we can detect. The inverse of threshold is called sensitivity, and that makes a little bit of sense if you think about it too, because if a threshold is very, very low, that means that the stimulus that you can detect is very, very small, right? Think of it for hearing as well. What's the weakest, if you ever had a hearing test, we're going to ask what's the weakest sound that you can detect. And if you have a low threshold, that means that you can hear very, very quiet sounds. That also means intuitively that your ears are very sensitive, right? So high sensitivity means detectable low thresholds. And the same applies for your contrast sensitivity here as well. That if you have a high contrast sensitivity, that means you can detect very low values of contrast, and you have therefore low thresholds. Here are some stimuli that will help us depict this. And if you were looking at this on a small screen, then maybe all the better to help illustrate the issue of visibility here. So on the top row of these top three stimuli at the top, those are all labeled from left to right as high contrast edges. And you should be able to see them, especially if you're on a nice, good, high quality, large screen. On the bottom, those three stimuli are low contrast, and you might notice that they are much harder to detect. So clearly in that case, the idea is just the difference between L and D is pretty reduced on the bottom here. There's another variable that's being manipulated here, though, that also helps kind of show an important point. As we go from left to right on the top, we are seeing a change in the size and spacing of these vertical stripes that are in the image. And these are referred to as sine wave gratings or spatial frequency gratings. And the reason they're called sine wave gratings is that if we were to make a graph of the brightness values, it maps out a nice simple sinusoidal function, as you can see in those graphs just below each image. And so the high contrast gratings have really large peaks and valleys in that graph. And if you look at the bottom, the low contrast gratings have much smaller peaks and valleys, because you're going to see then that the brightness doesn't go up very high and the darkness doesn't go down very low. It doesn't, not as drastic of a change in brightness values. But as we go from left to right, what's changing is the frequency of the sine wave, right? And so we see the peaks a little bit more spaced out on the left-hand side, where we have low frequency gratings, and then we have very densely packed stripes corresponding to a high frequency grating on the right. And you might then imagine that both of these variables relate to the detectability of the stripes, right? So certainly as we go to low contrast, it's harder to see the stripes. But as we go to high frequencies, we also have some difficulty seeing the stripes. And high frequencies is really just a fancy mathematical way of talking about the amount of visual detail that's present, right? Reading the fine print, so to say, involves reading high frequency patterns. And so in this situation, on the top, you might be able to see all three of those stimuli. And by saying see them, that you can actually detect the black and white vertical stripes that are all high contrast for both low, medium, and high frequency gratings. But on the bottom, you probably should see the low and maybe even the medium frequency gratings, but it might be much more difficult to see the high frequency gratings at low contrast. And so this is another way of thinking about the contrast sensitivity function, is a relationship, an interaction between spatial frequency and brightness contrast as well. So what this also means is that, as a lesson for visibility, high contrast is always better, and low spatial frequency is always better. And as you change these, you're going to impact visibility in one way or another. Now, because I noted that color impacts brightness, color also impacts visibility, because color impacts contrast, right? So again, just like brightness values for different colored patches can be kept the same, and still some colors will appear to be brighter than others. This also means that certain color contrast effects are more noticeable for others. And so what I've done here is I've created a different kind of color screen, in which I have a yellow text on a blue background. And I've chosen this because it's been known for a number of decades now that when it comes to color contrast effects, having that yellow on blue is a really nice contrast that is easily detectable by the human visual system. And it tends to result in a very high contrast pattern that can be easily detected. There were many computer software packages, especially back in the 80s and 90s, that tended to rely on a default yellow text on blue background. I think some of the earliest word processors did this. And that's because it was just known that yellow text on a blue background was easier to read than, say, black text on a white background, or white text on a black background, or any other kind of contrast that you might choose as well. And this persisted for a while, but here's another curious lesson in human factors. Even though objectively speaking, the yellow on blue was more visible and easier to read, people didn't like it. And something else that's important, say, thinking about a word processing program, like back in those days, it was probably WordPerfect. But now we have Microsoft Word, or any number of similar versions and variants of that, such as Open Office, or Google Docs, or Apple Pages and whatnot. And they all tend to default to the standard black text on white paper. as a metaphor, essentially, right? And that's what that really is that most of these word processor systems essentially now work as metaphors. When we are writing or typing, we tend to expect to see black ink on a white page. And that's what we normally are used to. And the word processors have evolved from their original appearance like this to having a document that really looks like a piece of paper contained within your window in the word processing application. And then that depicts the black text on white paper exactly as it would appear as if you were typing on a typewriter, or if you were to print out your document. It's giving you essentially a good, accurate preview of what it will look like when you print it out. And this appears to be more preferable to users for several reasons. One is that perhaps that's what they want, is they want to know that they're trying to make a document look a certain way. So they want to see it in the word processor exactly as it will look when printed out. And being able to achieve that is a different goal than just purely having a visible text on screen. And the other thing is that when people first started using computers, we wanted to create an environment that made this computer experience easy for them to understand and easy for them to learn. Just imagine, somebody in 1989 who had never really been in front of a computer in their entire life, and they're given the screen and the keyboard, and they're expected to start typing up documents in WordPerfect. Well, maybe it was a little bit strange to them because they didn't really see in their mind a real meaningful relationship between what they were typing on screen and how that might appear on a printed document. So by ensuring that the metaphor of the workspace, that is the virtual space that you're working on in the word processor environment, more closely matches your experiences and your expectations with documents, then that results in more user satisfaction and easier to learn systems. And so despite the lesson of human factors is that moving from what might be objectively better and from a certain perspective, the yellow text on a blue background was abandoned early on simply because of user preferences, right? And user expectations for how things ought to work. But also worth noting here that I have some other words in different colors here, right? And you can tell right off the bat that some of these colors simply just don't pop out as easily as the yellow text does, because again, the yellow on blue just has a stronger contrast effect there. So color contrast is very much just as important as is brightness contrast. We've already mentioned the importance of spatial frequency and the size of the detail. And that also is worth mentioning, by the way, is really where a person's visual acuity comes into play, right? So people who have poor visual acuity and may need visual correction, such as being nearsighted or farsighted and needing the appropriate corrective lenses for that, will have difficulty seeing objects that have small detail. It just in general, of course, large detail is easier than small detail. And I'm trying to capture that even with my text on that screen, right? And even when I have bolded at the bottom, that contrast is important, right? So by making things bolder here, we have slightly more contrast, and larger text, meaning large and high contrast, all come together to determine our total visibility here. Now, something else to think about is, I said earlier that the visibility of a surface, the large detail, low spatial frequencies, high contrast, that's all good. But when we measure these abilities, we could test this with people who are sort of young, healthy, no visual impairment, and therefore have visual systems that we would expect to be operating at their peak. But even in that situation, it's not as if those such individuals have a visual system that's always operating in the exact same way. And so something else we need to know about visual systems is that they vary in their performance over time as a function of what we're going to call the adaptive state of the neurons inside of the eye, right? So we have millions of photoreceptors inside of the eye. Photoreceptors are neurons that are specialized to undergo chemical reactions in the presence of light. And that triggers action potentials that transmit information back to the brain. And so, of course, the sensitivity of these photoreceptors is what is important for triggering the visual signals that are transmitted to the brain that will then involve perception of visual stimuli. We have two kinds of photoreceptors, rods and cones. What we know about rods is that they are primarily used in low light environments because they are actually very, very sensitive to light. So they have very low thresholds and therefore high sensitivity to low levels of illumination. And because they are so sensitive that in a brightly lit environment, they are essentially non-responsive because they're essentially being flooded with too much stimulation and they don't have a chance to recover, because every time a neuron fires an action potential, it has to go through a refractory period before it can fire again. And if you overstimulate neurons to the point that they can't really go through this refractory period and regenerate their action potentials, then they will simply shut down. And that's what's happening with rods. Simplified version, at least, of what's happening with rods in bright environments is that they really cannot function. But in low levels of illumination, so if you're just sitting in your house late at night and you turn off all the lights, one of the things that you're going to notice right off the bat is that you can't see anything, right? But gradually you start to adapt to that darker environment. So this process is called dark adaptation. And what's happening is that your rods are gradually recovering from being overstimulated and flooded with all of that light. And they are sort of gradually regaining the ability to function, but it takes several minutes for this to occur. And so as the rods gradually recover, you are adapting and you start to see better and better, but at least up to a point, right? So at a certain point, which is going to take maybe around 20 or so minutes, it's on the very next slide here. So it shows about 20 minutes. We're seeing some level of leveling off of our sensitivity there. I'll come back to that. That's when the rods are essentially now operating at their peak level of functioning here. But then we see something else with the cone system, right? So the cones are a different kind of half of our visual system that works better in those brightly lit environments, like just in a general room with the lights on or outside in the sunlight. And so in that situation, because the cones are essentially not very sensitive and they have a very high threshold, they really need that brighter light in order to function. And when you turn the lights off, suddenly there's not enough light to stimulate the cones. And so the cones are kind of shutting off at this point once we get into the dark. And then what we're seeing is that gradual improvement in vision after 20 minutes is primarily a function of our rods kind of managing to turn themselves back on in about 20 minutes time. But a couple of other things we want to notice about the rods versus cone, besides their relative sensitivity, is the kind of information they provide the brain, right? So it's obvious that in brightly lit environments, we see things as having, we can see the fine detail, we can read a book, right? And we can see color quite clearly, assuming no color vision issues as well. Some people have various forms of color blindness as well. That might be worth noting also. But once we turn off the lights and we switch over to rod vision, we can't see very good detail, right? You can't read a book in the darkness, and you don't have very good color vision, if any, right? Everything is just basically black and white and shades of gray in the dark. And that's because your rods are the dominant visual system at this point, and they cannot process color information. So that's these are all relevant points here. So let's take a more detailed look at the dark adaptation curve. And so one thing to point out here is that there are three different curves on this graph, right? We have the solid line, and the solid line represents our actual sensitivity to light at a given time, right? And so if we start on the far left-hand side of the graph, here we're at 0 time in the dark, or essentially imagine that we have our lights on, right? And so that means our sensitivity is actually not very good, because once we turn all the lights on or we're out in the sunlight, our eyes are adapting to this bright environment. And to adapt to the bright environment means to sort of become less sensitive. Uh, think of it this way. After you spend 20 minutes in the dark and then you just suddenly turn on all the lights, uh, that oftentimes hurts your eyes a little bit, right? And that's because your eyes have become very sensitive to low levels of light. And when we suddenly jump to bright light, that's too much light and it floods your eyes and it's almost painful, right? So that's what we're in here in the brightly lit environment, is that once we spend enough time in the bright environment, our eyes have sort of reversed this process of dark adaptation, and it's called light adaptation, and we get more used to functioning in the bright environments. But as soon as we turn off the light, and now we're going to start counting, 1 minute in the dark, 2 minutes in the dark, one of the things that we're going to see is that, yes, our cones do have the ability to adapt a little bit, right? And so that's what we're seeing here, is that that dark line mirrors the heavier dash line because the cones are functioning better than the rods are here, right? And they're a little more sensitive and they're functioning better. So we're going to continue upwards to nearly 10 minutes as the cones gradually get better at seeing in the dark. And of course, you see there, the rod line is that other dash line with the smaller dashes in it. And in the brightly lit environment, right, the rods are simply just not functional at this point, right? They're just have such low sensitivity that they can't function whatsoever. So the rods are continuing to adapt, but obviously they're adapting at a much greater rate than the cones are, and eventually they catch up to the cones. And what we see at that little point in the graph where the lines intersect, labeled the rod cone break, is that at this point, the rods are the ones that now become more sensitive than the cones. And this is when we switch from cone vision to rod vision. And so it's at this point, around 7 or 8 minutes after turning off the lights, that we might notice a more rapid improvement in our ability to see in the dark. And that's going to continue on up until, as I previously noted, about 20 or so minutes that we achieve our maximum dark adaptation. And the rods just won't get any better than that after that point. Now, a couple of things we also want to say about rods and cones here is how is it that the cones can process color, but the rods cannot? Well, one thing we want to point out here is that there are actually 3 kinds of cones. And so we have what we will label as S cones, which means short wavelength cones, versus M or medium wavelength cones, and then L for long wavelength cones. And the idea is that each of these 3 different types of cones works together as part of the overall cone system to combine their responses. And it's these different combinations of responses across the 3 kinds of cones that gives us our ability to see color. So imagine if you're looking at something that falls somewhere in the 500 nanometers wavelength of light here, right? What's going to happen is that's clearly in the green end of the spectrum. And so that's going to activate some of the M cones, right? We see the M cones sort of have their best response to light around 531 nanometers. But that doesn't mean they only detect light at 531 nanometers. It merely just means they're most sensitive to light at 531, but they will still respond in a sort of a medium fashion, I guess you could say, to light at 500 nanometers. And likewise, the S cones, their peak response is 419 nanometers, but they do detect very weakly light at 500 nanometers. So you might get a weak response out of the S cone system. And then likewise, out of the L cone systems, their peak response is 559 nanometers, but they will still respond in a medium way to light at 500 nanometers, kind of a low medium way, right? And so being exposed to 500 nanometer light means that we're going to get activation of all 3 cone systems, but we're going to have differential activation of all 3 cone systems. And that differential activation is now a code that can be sent to the brain as a way of telling the brain, this is the color that we're dealing with here. 500 nanometers are green, right? And then likewise, when we shift a little to the left of 450 nanometers, we're going to get a very different combined response out of our three cone systems. If we go all the way to the right at 650 or 700, we're going to get very different as well, right? So the idea is that by combining these different proportional responses across the three kinds of cone systems, this is what gives us our ability to detect all of the different colors that we can see. This is called trichromaticity theory, that there would essentially be three primary colors, a red, green, blue, or RGB type system. And by combining the three primary colors, the RGB, we're going to be able to essentially replicate all of the visible colors that humans can see. Now, in contrast to that, let's look at the curve for the rods, which is also included in this graph. So the rod signal is processed separately by the brain than the cone signal is. And the rods all work exactly the same. We don't have different kinds of rods, just like we have with cones. And they have a peak response at 496 nanometers. So that means that if I'm looking at something in the dark using my rods and it happens to fall at 450, my rods will respond to it, maybe weakly, but they will still respond to it. If I'm looking at something that's 550 nanometers, I'm also going to get a response from the rods that might be roughly equally weak compared to the 450 stimulus. So how does my brain know the difference between this kind of a blue-green 450 nanometer stimulus versus a yellowish 550 nanometer stimulus in the dark using my rods? And the answer is it clearly doesn't happen, right? My brain cannot distinguish those two stimuli and therefore treats them not as color at all, but rather simply just two surfaces of a certain brightness. And that's important here as well, because think about this. If the rods respond best to a stimulus around 496 nanometers, does that mean that a green object seen in the dark will not appear green, but might be easier to see and therefore appear to be a little bit brighter? And the answer is clearly yes, right? And all of four of these curves, by the way, might help us explain why some colors are brighter than others. So on the previous screen, when we looked at all those different color patches, some appear to be brighter than others, and that might just be because the cones respond a little bit better to those wavelengths compared to some of the other wavelengths. And in the darkness, this will change a little bit. So you can try this experiment if you want to. Get a green object and a red object that are roughly equally bright, and then sit them on a table, and then sit in the darkness for 30 minutes until you're fully dark adapted, and then look at these two objects. And what you should find is that the green object appears to be brighter and easier to see compared to the red object, which might appear to be very dark in your environment. So that'll confirm perhaps that your rods do work better in that range, but you don't encode it as color, but just as variations in brightness, because the rods respond a little more strongly to that. Now, sometimes is after we spend some time in the dark and we get fully dark adapted, this means we can see well in the dark. And maybe this is something we want to have. Think about driving at night. If you're driving at night and you're out on the open road and there's not very many lights around, so you become adapted to that darkness and you can see a little bit better. And then what happens is that maybe you drive through a well-lit environment for a minute, and so now this ruins your dark adaptation because now your eyes shift back to functioning in brightly lit environments, and then you get through that area, and then you're back in a dark environment, and you might have a period of time where you have a little trouble seeing as well, because you have to recover your dark adaptation. So maintaining dark adaptation might be useful for certain cases like that. Now, in this situation, we're looking at the bridge of a submarine, and we're noting that they are using red light inside the submarine. Why are they using red light? Why do they need to be dark adapted? Well, the dark adaptation really only applies to one person. So imagine you are on maneuvers in your submarine, and you are you have to, it's nighttime above the surface of the water, right? And somebody has to look up the periscope because maybe you're looking for an enemy target. And so to look through the periscope in a darkened open ocean environment where it's going to be very, very dark there, you're going to want to be dark adapted so that you can see anything, right? But if you are looking through the periscope and then you leave the periscope and you enter the bridge and it's brightly lit, it's going to ruin your dark adaptation. And then when you go back to the periscope, you're essentially not going to be able to see anything at all for some period of time, right? So what we want is we want our periscope operator to maintain a dark adapted state. So wherever that periscope operator has to do their job has to be illuminated in red light so that we don't damage their degree of dark adaptation here. And of course, the red light is sufficient for all of the other officers on the bridge to be able to function and to do their jobs. So it provides enough illumination for them, but it's primarily for our periscope operator that we are doing this, right? And let's go back for a second, right? Why red light? Because again, if I come back here to the rod sensitivity curve at 496, which is green, clearly exposing rods to long wavelength light above 650 nanometers will not stimulate the rods whatsoever. And therefore, this will not affect their sensitivity or their adaptive state. Now, I'm mentioning this also because in recent years, we've seen a lot of emergency vehicles, especially police cars, include blue lights on their cars in addition to the classic red lights. And so the combination of the red and the blue are used to distinguish police cars typically from other emergency vehicles. But now we have to ask the question, does the presence of this blue flashing light, now again, you're driving in a dark environment and you pass a police car. And if this was 50 years ago, the police car may have been flashing red lights and that might not affect your rods very much. But now this police car is also flashing blue lights. Does this really negatively impact the dark adaptive state of drivers who pass by the scene where a police officer has somebody pulled over? Well, good chance, right? So that means that now after immediately passing the police running their lights, we might have a temporary period where we might have an increased risk of an accident because our vision is impaired after seeing these bright blue lights. All right, so on to acuity next, right? So for acuity, this is where we're going to talk about our ability to see the fine detail, the high frequency gratings in those sine wave gratings, right? So we can test that using those spatial frequency gratings, right? Just by presenting a stimulus that has very high frequency gratings, very narrow vertical black and white stripes. Although classically in a lot of vision tests, we don't use those, right? And we can use those in research purposes because we can very carefully control the level of detail. But in more practical purposes, such as say going to the doctor and they want to do a fairly quick and easy way of detecting your visual ability, we're going to use something called the Snellen eye chart. But we might also have other cases such as the Vernier scale, which I'll show you in a second. So this is the classic Snellen eye chart, right? And so the idea here is we see different levels of visual acuity. If you can read line 8, you have to be at a certain distance from this. It has to be printed at a certain size and stand at a certain distance. Then if you can read line 8, you have 20/20 vision, right? So what does that number mean, 20/20, in the first place? Well, this is actually a standardized measurement here. So according to 20/20, the numerator value refers to the level of detail that the subject who we're testing can see at a distance of 20 feet. The denominator tells us the level of detail that the average person can see at that same distance. So if you're at 20/20 vision, that means that your vision is essentially normal or typical, the same as an average person, right? So that means the level of detail that you can see at a distance of 20 feet is equal to what the average person can see at 20 feet. If you have very poor vision, such as 2200 vision, where you can only read the large letter E at the top, that means the level of detail that you can see at 20 feet is more similar to what the average person can see at 200 feet. And of course, if you imagine an average person's vision from 200 feet away, obviously the visual quality at that distance is not very good. But for a person who has poor vision, then that's what their visual world is like, even at 20 feet, right? So clearly 2200 vision is not very good. 20/20 is average. It is possible to have better than 20/20 vision. And that's what being able to read lines 9, 10, and 11 could reveal, for example. Now, this is a measure of vernier acuity, right? And so what we have here is two line segments, right? A top and a bottom line segment, but all vertical, But what we want to do is we want to introduce a lateral shift in those line segments and ask someone if they can detect that little lateral shift in the line segment. The stimulus in the middle is perfectly aligned, right? And we can do this in a systematic way so that we can shift the line segment over by a very tiny fraction, maybe in an image like this, a couple of pixels, right? And keep increasing that lateral offset until someone detects, oh yeah, now I can see that they're not aligned. Why is this possibly interesting? Well, this actually corresponds to a lot of real world situations. If you've ever done something like operated a padlock with a dial on it, right? You got to dial one number and then another. Then what you have to do is you have to align the hash marks on the dial with the hash marks on the outer number scale to ensure that you get the numbers lined up correctly. And if you don't do that well enough, then you didn't select the right number and you won't unlock your lock. I had also mentioned in one of the previous videos about the possibility of misreading the speedometer in your car, right? That's doing when doing a task analysis for speed maintenance. One of the things you have to do is check your speedometer and accurately perceive the indicated speed. And typically what this means is that in a traditional speedometer display, you're going to have the needle that goes up and down the display against a vernier scale, right? A bunch of hash marks that say 40 mph, and then you got to have some lines, and then it's going to say 50 mph and so forth, right? And so being able to accurately detect the presence of that needle relative to the vernier scale behind it is relevant to vernier acuity. And if your vernier acuity is poor, this could increase your risk of misreading the speedometer. This is why also, though, a lot of cars nowadays include both the classic kind of what we'll call an analog vernier scale, the needle against the scale, but also a digital display that will just show your speed, and it'll just show the numbers 50 mph on screen. And you might think, why not just switch to that, right? Why not just switch and always just show 50 mph on the dash display instead of using the needle, if that's kind of less ambiguous, perhaps, right? And we don't have to worry about someone's vernier acuity. Well, maybe now we have to worry about their Snellen acuity to read the numbers, although we're probably going to see that Snellen acuity and vernier acuity are highly correlated with each other. But there's something else that we lose when we switch to the digital to display. So detecting my speed is one thing, which is simply just to know where the needle is on the vernier scale. But it's also sometimes nice to detect the rate of change in my speed, aka acceleration and deceleration. And when I watch the needle go up on the speedometer or down, it does so at a particular rate that is directly proportional to my car's acceleration. And that's easily seen. I can just see that needle move up and down at different speeds. But when looking at a digital display for your speedometer, and it shows 50, and then I start to decelerate, if I let off the gas pedal and my speed is going to start dropping, obviously those numbers are going to start changing, right? But it's really hard to detect the rate of change as you just watch the numbers switch from 50 to 49 to 48, right? It's just harder to see that. But watching that needle drop, that really gives you a much better sense of your rate of deceleration. So there's quite a bit of advantage to including the traditional needle vernier display in a speedometer. All right, now to wrap up our vision content here, we want to talk last about depth perception. So as I mentioned at the beginning, visibility is important for vision, but because vision is a spatial sense, we also need to take into account whether people can accurately perceive the size and distance, aka the spatial scale of the world around them, because accurate perception of spatial scale certainly will be important for accurate control of movement, right? In order to reach out and touch an object, to select a control and push a button, I need to perceive where it is pretty accurately. If I'm driving a car and I need to stop without colliding into something in front of me, I need to perceive my distance and stopping rate accurately, right? So there's a lot of depth information that we need to think about here, and we need to be possibly worried about situations where depth perception could be impacted by something, right? So we want to think about all of these different ways that we have to move around and interact with objects and the importance of spatial information and how do we possibly interfere with spatial information. So one of the things we have to do is we have to understand the basics of how we perceive depth in the first place. This is something of a common long-standing concern in visual perception research, because the trick here is that when we think about perceiving a spatial environment, we're thinking about perceiving a three-dimensional environment, right? And by three-dimensional, I would mean that any object, any three-dimensional object has three spatial dimensions. It has a height, right? It has a width, but it also has a depth. And that depth is important here because not only does that tell us about the three-dimensional shape and size of any object we're looking at, but it also tells us about how far away things are from us, whether something could be a few feet away from us or several feet or meters away from us. And perceiving that third dimension, the depth dimension, is tricky because we have to ask, how does the visual system perceive all three dimensions? When if we look at the visual system in detail, we realize that the visual stimulus appears to be a two-dimensional image. And by that, I mean, we have to think about the retina in the eye. So I don't have any diagrams in here of eyeballs or anything. I don't think we need to get into the details of this too much, but the problem is that our eyes collect light, right? The cornea and the lens collect light from the environment and project those light rays onto the interior lining of our eyeballs. That's called the retina, and that's where all of the rods and cones are found. And so the interior lining of the eyeball, the retina, is essentially then flat and it works exactly like a projector screen that projects an image onto, say, just a screen like in the movie theater, right? But that projection is flat and two-dimensional, where objects in the projection have a height and a width, but they do not have a depth, right? That depth dimension is missing in the 2D retinal image. And then the next question then is that given this sort of two-dimensional input to the visual system, how does at a perceptual level, how does the brain recover the missing third dimension and perceive a three-dimensional environment despite 2D input? Well, we have, as a proposed solution, what are called depth cues. And depth cues kind of span a few different types, right? So we have some things that can be essentially what are called anatomical cues or physiological cues. And these rely on kind of things that are considered extra-retinal. And by extra-retinal, I mean things that don't actually originate from within the retinal image itself. And one of these is called accommodation. Another is convergence. And then we have the issue known as retinal-based depth cues. And so these are based on specific visual patterns that occur on the retina itself. That would be binocular disparity, but also what are known as the pictorial depth cues. By pictorial depth cues, and I have those listed down here as linear perspective, interposition, shading, and texture gradients. These are the kinds of depth cues that can be detected in pictures, right? So if you're learning to draw in an art class and you're being taught how to draw in depth and create a nice impression of distance and spatial scale in your drawing, you are typically taught pictorial depth cues, right? These are ways in which you could convey the impression of depth. And so this is thought here that the brain essentially does the same thing, is that the retinal image contains a lot of those pictorial depth cues, and the brain learns how to interpret the patterns in the image in the same way that a person looking at someone's drawing can interpret the drawing and understand that it's really a depiction of a three-dimensional scene, even though it's a drawing on a two-dimensional canvas. So let's talk about some of these depth cues in particular here. I don't have a picture for the accommodation, but that's somewhat simple. I don't think we need a picture of it necessarily. What's going on with accommodation? And accommodation is the name of the process for when our eyes actually focus. So the lens in your eye, like the lens in any particular optical device, like a camera or binoculars or telescope or microscope, it has to adjust its thickness based on the focal depth, right, or the distance, the viewing distance. And so the lens in your eye is adjustable, just as is the lens in any other device like a camera, right? And using a camera analogy for the eye, it's not the greatest, but it's going to help us in this regard, I think. So what we're going to say here is that when the lens itself adjusts, which this is an automatic and reflexive process, but it is controlled actually by a muscle. So we have a small circular muscle inside of the eyeball called a ciliary muscle. And the ciliary muscle has to constrict and contract down when we are looking close up. And that creates a little bit of muscle tension inside of the ciliary muscle when we're looking at something that is close. And so now the hypothesis is that the muscle tension, just like any muscle on our body, if we tense that muscle, we can feel the tension. And so now the claim here is that maybe we can feel the tension in the eye muscle, the ciliary muscle inside of the eye that controls the lens. And maybe we don't consciously feel it quite so much, though a lot of times you might notice that when you are looking at something close up for a long period of time, your eyes become fatigued. And that could, of course, involve some fatigue of the ciliary muscle. But anyway, if the brain has the ability to detect variations in the state of the ciliary muscle when it's contracted for close-up viewing versus when it's relaxed for far-away viewing, then that could provide information to the brain about the distance of the object that has been focused on. Right, so the eye is essentially just automatically and reflexively doing its job to detect objects at different focal lengths and focal depths. But that can also then simultaneously provide feedback to the brain to say, this is close up, this is far away. So that could be useful information. But as it turns out, accommodation only provides a very, very rough source of information about distance, right? Just generally speaking, a very rough approximation of things that are close versus far. And it's not very good at precisely localizing exact distances to objects. Convergence works quite a bit better. So let's take a look at this next picture here. So convergence now requires two eyes to work together here. And so we see that this kind of depth information would only work when you have two eyes that are pointing more or less in the same direction. That is, for humans and primates, we have eyes on the front of our head that kind of can work together pointing in the same direction. This is not going to work very well for animals that might have eyes that are more up to the sides of their heads that kind of point in different directions. So what's happening here, and you can kind of see from the diagram, that when the person is looking at one object that is farther away, that the two eyes both have to point at this object, right? And that's what those lines are. They're showing kind of like the gaze angle where the eye has to point in that direction to be able to look at that specific object. And since the two eyes are pointing in the same location in space, we can make an angle out of those gaze angles, right? And that's the angle A here. And that kind of reflects the degree of convergence. That is how much the eyes have to converge together to look at this object. If we move the object closer, now the divergence angle increases, right? The degree to which the eyes have to turn inward together to really focus at that one same point in space creates a much larger angle. That's called the divergence angle. And here we see that the divergence angle B is much larger than the divergence angle A. And so the claim here is that this provides some fairly good depth information, right? That our brains are actually very good at detecting differences in the divergence angle between the two eyes. What's also perhaps worth noting here is that I can treat those two sight lines there as the sides of a triangle, right? And so imagine connecting the base of that triangle by drawing a vertical line between the two eyes there to connect the two ends of those angles. And at that point, I could use trigonometry to triangulate the height of the triangle, right? And so this could actually suggest that if we knew one of these, any one of the spatial dimensions of this triangle, such as maybe the distance between the two eyes, that's known as the IPD or interpupillary distance, that we might be able to triangulate distances in a much more precise and accurate way. And not simply just know that one thing is closer than another because its divergence angle is larger than another, but maybe even compute exact distances to objects here using convergence. Now, the third cue here, this is the one that we consider more of a retinal-based cue because it relies on differences in the locations of points on the retina themselves. And again, though, this relies on having two eyes that work together. So this is called retinal disparity and/or binocular disparity. And what we're seeing here is imagine a situation where you're looking at a tree off in the distance, and you can try this and if you have a tree to look at, but maybe any object that's maybe on the other side of the room. But hold up your finger in front of it and try to align your finger with that distant object. But what you're going to notice is that if you keep both eyes open as you do this, and then if you close your eyes and alternate them left and right, you probably can't see that's what I'm doing in the screen here, but I'm alternating my eyes. What's going to happen is that that's going to cause my thumb or finger in this case to appear to jump back and forth, right? Because what happens is that when I line it up with my right eye, then what actually happens is that the right eye is looking at it so that the finger is a little bit to the left of the distant object that I am focusing on. Whereas from my left eye's perspective, the finger is a little to the right of the distant object. And so what happens here is that the spatial this kind of spatial organization and this difference in the way in which the finger relative to the distant tree is projected to the right eye is different from the left eye. And the brain is going to, again, be able to use that kind of disparity or difference between the two retinal images to compute the exact distances to these objects. This is, again, the kind of stuff that when we were talking about virtual reality in the previous recording, this is how we simulate good, strong depth information in virtual reality, because what we're going to do is we're going to ensure that the scene that is drawn for your left eye is appropriate to that kind of left eye's spatial view on the world, which is shifted over a couple of inches from the right eye's spatial view in the world. And so by showing those different kinds of scenes to each of the two eyes, we can kind of replicate the kind of disparity information that would normally be present in a real world environment like that. And you can create a very nice, strong, compelling impression of distance in VR using those kinds of disparities in the two images. Now, as I had mentioned, the other four cues listed here are pictorial cues. So these are the kinds of cues that are present in patterns. So this is linear perspective here. This is maybe a little more than linear perspective going on here, but it's hard to sort of control all of these all at once. So the way we usually talk about linear perspective is to say that lines that are parallel in the world, in the three-dimensional world, are not really drawn as being parallel, right? If you were to draw railroad tracks or a road, for example, and if you're learning to draw, then you would not try to draw them parallel with each other. Instead, to create that sense that they are receding away in the distance, you have to draw them as actually converging together gradually. And they're actually pointing to the horizon. So this kind of pointing to the horizon is part of the concept of linear perspective, is that all of these parallel lines, which is the rails and the railroad tracks here, have to, even though they are parallel in the real world, in the three-dimensional world, they are drawn in this way. And so that same thing would happen if you were standing on the railroad tracks, right? Is that the image projected to the retina inside of your eye would be equivalent geometry here of a scene that shows the rails as converging to the point in the horizon. Likewise, we also see other things converging to the horizon line, like the edges of the railroad ties and any imaginary lines that connect those trees. Those would all be lined up and pointing to the horizon as well. Something else that's worth pointing out, though, is that there's an additional cue here called a texture gradient. And this is the fact that those railroad ties are all the same length, but they appear to get shorter and shorter the further away they are. And the spacing between them should all be equal spacing, but that spacing appears to compress the further away we are. And if I jump to some pictures here, here's a cranberry bog, right? And so here's another texture gradient, because we would imagine that the size of the cranberries are all roughly equal across the entire bog, and that the spacing between them is all roughly equal. But what we're seeing is a compression that occurs, so that the further away we go, the cranberries appear to be smaller and more densely packed together. And that's not true in the real three-dimensional world. It's only true in the way it's rendered in the two-dimensional projection here, right? And so that texture gradient also is a way of capturing depth information. We see that both with the cranberries as well as here with our railroad ties. Right? Interposition is listed here. Interposition is capturing the idea that when an object is closer compared to another object, then it's going to partly cover up the more distant object, right? And so we might perceive the triangle is closer than the circle, and the circle is closer than the square because of that interposition. And that's a little vague as a depth cue, right? It doesn't specify exactly how much distance between the surfaces, but at least it gives us some kind of ordinal depth information. I didn't include a picture for shading, but that's one of the other choices that are listed here. We might get a little shading from this picture, right? The idea is that a little bit of shading information might tell us about the position of these objects relative to a light source. So we kind of get the impression that there's a light source to the left, and that tells us about where things are, and it's kind of in a spatial layout kind of way as well. So what about the human factors and implications of distance and depth perception here? Well, one of the things that we have to be concerned about is that whenever we look through a medium, that is, we look through a lens, we look through a window, we have some light refraction that's going to occur, right? And that means the light rays may be bent in certain ways. And if there's some curvature to the lens that we're looking through, this could actually distort sizes and distances quite a bit. And if you've ever been in a big pickup truck and you have those big side mirrors and there's one mirror on the bottom that's curved, and there's a little note on the bottom that says objects are closer than they may appear, or something like that, right? That's because these mirrors are distorted in a way that can distort distance. So why would you include these mirrors? Well, what these mirrors give an advantage of here is that because in a big truck, it can be sometimes hard to see all the way around you. Then having those curved mirrors on your side mirrors will increase the field of view that you have, so that you can better see if there is a possible car in your blind spot, and as you try to change lanes, for example. But it can then simultaneously cause you to not be able to exactly see how far away that car is from you. And so you have to take that into account and think that, well, there appears to be a car in my blind spot and I can't tell for sure, but I'd better be careful and safe at this point and not try to perform any lane changing maneuvers, right? But that's important, because without that kind of acknowledgement to the driver to know that maybe the distances might appear distorted, a person might end up making some mistakes here. Something else we know is that if we are to look imagine looking through a tube, right? If you're just looking through your hands like this, right? So we have a restricted field of view. We don't have the full range of our vision that we normally would. That's known to create some depth compression, really, what's happening there, right? Depth compression means that everything appears to just be a little bit closer together. All distances end up a little compressed. And that might mean that any situation where we have to look through, not just looking through a tube, that might not be very common. Maybe looking through a telescope or binoculars could be somewhat similar to this. But maybe in virtual reality, I think I mentioned that in the previous notes, that can cause it, because of the restricted field of view, might cause a little depth compression. But maybe even looking through small windows, right? So if you're inside a vehicle and you have to look out a window, but it's a small window, right? What is this? Maybe it's a plane, specialized aircraft of some sort. You have small windows to look out. Maybe distances might be impacted by that. Why is this happening? Well, it might be because our ability to detect some of those linear perspective cues and texture gradients might be just less visible when there's less of the overall scene to be able to detect. Maybe because it interferes with interposition, and therefore the different occluding edges between interposed objects may not all be visible. And so there's a lot of things to be concerned with here. Other limitations is that some of these depth cues, like convergence, accommodation, and binocular disparity, really only work in what we're going to call near space, which is within a distance of 1 meter, up maybe to 3 or 4 meters at most for disparity. But with convergence and accommodation, we're really only talking about working well within about a meter of space here. And that means that while we have fairly good depth perception up close, and that makes sense from a functional perspective, because up close depth perception is really important when we want to work with our hands and reach out and pick things up. Further away distances, our abilities to discriminate depth might be a little weaker. And so that needs to be accounted for, that just in general with human depth perception, It is superior when working in near space compared to far space. As I noted before, again, with VR, there's a variety of known distortions of depth perception in virtual reality. Some of it could be because of restricted field of view. Some of it could be because of other kinds of poor renderings of textures and linear perspective. Some of it could be because of the lack of good accommodation cues, perhaps, right? Because the actual lens or screen, sorry, in the HMD is only a couple inches in front of your face. And so you might be trying to look at an object that's virtually depicted as being a meter away from you, but your eyes are still accommodating a lens that's just 2 inches in front of your eyes. And that creates a cue conflict, right, between what accommodation says versus what disparity says. And that might create some sort of weird distortion of distance. And then there's also the lack of feedback, right? The fact, like I had mentioned in previous lectures, about the fact that you can't reach out and grab virtual objects and have that physical contact with them. And maybe there's some importance of calibrating visual depth perception that requires that kind of constant haptic contact with the world. And once we go into a virtual environment, we lose that calibration and our depth perception is distorted. So there's a lot of things that we have to be concerned about with the whys. But just in general, the implications of that means that anytime I have somebody performing tasks in virtual reality or augmented reality, I have to be concerned about whether or not they can perceive distance correctly. And if I have them do any kind of task in which spatial scale perception is critical, it is very critical that they accurately perceive size or distance, then I might anticipate the increased risk of errors at this point, right? So those would be important concerns. Last up, though, it's worth them pointing out here that I have other depth cues worth talking about, essentially motion-based cues. And so everything we've talked about so far implies sort of like the eye, kind of like a camera taking snapshots of the world and taking pictures, and what kinds of pictorial cues are there. It turns out, though, there's other information that's available when we are moving. So one example is motion parallax. This is easy to observe, right? If you are driving in a car, riding in a car as a passenger is a better case here. So if you're driving past a field, just pay attention to when you look at the side of the road, everything on the side of the road appears to be zipping by super fast, right? It's just like a blur, especially if you're going fast, like if you're on a highway and you're going 70, right? But if there's a field there, that means you can see maybe a good quarter mile or half mile across the field, and there could be a row of trees, let's say a quarter mile away. And those trees don't appear to be zipping by super fast like the stuff on the side of the road, right? They appear to go much more slowly. Even though you're still driving 70 miles an hour past all of those items, the stuff that's close has a much higher optical velocity, is the term, compared to stuff that's further away. And that differential motion between near versus far is called motion parallax. And it's a function of the viewing distance. So by moving in the environment, we create motion parallax. We create this differential motion between near and far objects. And that can play an important role in our abilities here now to detect distance. Optic flow is very similar to this, right? Optic flow captures not just the entire concept of motion parallax across the entire visual field, but also captures a variety of different other patterns in the visual motions that occur when we are walking or moving around in our environments that reveal all kinds of extra important spatial information. So here's one example of motion parallax and optic flow that might be the perspective of a pilot approaching a runway. And this was important because this is one of the early discoveries in human factors research that was discovered by one of the originators of the optic flow concept, perceptual psychologist named James Gibson. But Gibson was also working in a human factors kind of context for the military in World War II. And they were noticing some of the struggles that pilots had when learning to land their planes because they couldn't get the plane lined up to the runway correctly and descend at the correct rate. And part of it was because they couldn't see the runway. You keep your nose up, you don't have a good view of the runway. And so Gibson was concerned with trying to improve the ability to detect this thing here. What is this thing? Notice these arrows that all appear to be radiating outward from that central point. So this is called an optic flow pattern. So this means that as you are approaching this, you're going to experience visual motion of the runway. As you get closer and closer to the runway, it will start to expand in your field of view imagine walking towards a door, right? And as you walk up to a door, it's going to expand in your field of view as well. And it's going to expand in this kind of radial symmetric way. And the central point of that radial expansion is called the focus of expansion, or it's a nodal point in the flow field. And that specifies your heading direction. And so if you want to know exactly what trajectory your plane is on as you are approaching and landing on this runway, then being able to see the focus of expansion and know that it is right there, that means that that's going to be your touchdown point, right? And if that's good, then you can keep your rate of descent where it is. But if you realize, oh, I'm not going to land where I hope to land, then maybe it means that you need to lift up and try to aim a little further out. Or if you realize that maybe that landing point is too far out, that means you're going to touch down too late and you won't have enough time to stop. So that means you have to abort your landing and climb and then circle around and try again. But if you can't see the focus of expansion as you are approaching the runway, it makes it a lot more difficult to regulate your landing and your approach as needed, right? So our goal here is to try to improve the visibility of the focus of expansion. The same might be true in driving, for example. This is fortunately not the case, that we don't have any things blocking our field of view in the front. We want to keep the field of view of the windshield in front of us open so that you can see the expanding roadway and other cars as you approach them, right? But imagine a situation where you're trying to drive something where you had some sort of occlusion in your field of view and you couldn't see right in front of you. That would make it much harder to regulate your steering. This is an image that it's not the greatest, but I think it tries to help us capture and visualize the concept of optic flow. So if you were walking over a flat ground and there were some visible elements on the ground, then the kind of motion that you would experience would be this kind of, again, a radial expansion of the elements along the ground plane. It wouldn't look like this on the pilot's view, because the pilot is kind of approaching this ground from above and everything is expanding out. But instead, in this case, as you walk over the ground plane, everything just kind of flows past you, right, from some central point. And that vertical little line on the horizon would correspond to our heading direction over the ground. This is another way to capture and visualize optic flow. So this is imagining what the optic flow would look like from the perspective of a bird flying over a plowed farmer's field. And these arrows that we are kind of trying to visualize with this imaginary hemisphere represent the optic flow of the ground that the bird is flying over. So as the bird flies over the ground plane, the bird will experience visual motion or optic flow of the ground. And the length of those arrows corresponds to the rate of optic flow, that is the speed, right? So things that are closer have a higher optical velocity and therefore have longer vectors. All of those vectors are radiating outward from a central flow point, a focal point, and that would correspond to the bird's heading, which is that large arrow right in front of the bird, right? It tells the bird where it's flying. So this, we don't need to go into all of the details and formalizations of optic flow, but there's quite a lot that we can do here. But the basic idea is that the flow pattern captures motion parallax, right? It captures differential optical velocities as a function of distance. It captures the focal point and the direction of heading, and it provides a lot of information about the spatial layout of the environment, the presence of opticals, and how to get where you're going and control your movement in the environment. And that's, of course, crucial, right? If we want to ensure that walking humans in particular can control their navigation in a cluttered environment, then the availability of optic flow information is pretty critical to that. And so anything that might disrupt optic flow and our ability to see optic flow patterns, such as walking in the dark, walking with goggles on, that might restrict our field of view and not be able to see the entire flow pattern, having occluding surfaces in front of us that prevent us from seeing the focus of expansion. All of those things could interfere with, again, locomotion in a cluttered environment. Well, I think we've done quite a bit, I think more than enough for one class period here. Might need to break that up into two, but otherwise, we're done with vision, and I'll see you next time.